Okay. So the open loop transfer function of a unity feedback system is given, which is okay. So this is the open loop transfer gain transfer function for the unity feedback system. Okay, and they're asking the range of k for which the system is stable. So we need to find for what values of k this system will be stable. First of all, we need to find the transfer function of the closed loop system, right? Because they are saying this is open loop transfer function. Now closed loop transfer function for unity feedback would be what? G by 1 plus G. Because okay, so whenever we say unity feedback system, it means that there is this GS, okay, and there's a negative feedback from the output. So when you write the transfer function of this closed loop system, now this will be this, right? G by 1 plus G. Okay. So when you solve this, now in the denominator it will come this s into s square plus s plus 2 s plus 3. Basically whatever is that at the numerator will come here. You can solve this, and we don't care about this, right? Because the characteristics equation will be given by this, and that will be required to solve the stability condition, solve for the stability condition. Okay, now how to solve this one? We'll use Routh stability criteria. Okay, so Routh stability criteria we'll use. What is it? Okay, let me show you. So first of all, you write this, simplify this. So this will become plus k. So this is the equation. Okay, let's remove all this now. This is not required anymore. We have got the characteristics equation. Okay, so once you have this characteristics equation, right? So now the Routh stability criteria tells you this. So you first write the coefficients of powers of s like this, right? And so on. And you write the coefficients of s to the power 4 first, and then the alternating coefficient, right? Okay, by the way, so all the powers of s should be there. If any of the power is missing, let's say this s square was not there, then we can right away say that the system is unstable. I mean, there is no value of k for which this will be stable. Okay, so the first criteria is that all the coefficients should be there. All the powers of s should be there. Okay, so which is there in this case. So we need to dig in further. 1, 5, k, and then the remaining ones, right? These two will write for the s cubes coefficient, so which is 4 and then 6. Now the Routh stability criteria tells you that this first column, right, all the coefficients should be of the same sign. Okay, now how to find s square? To do this, what we do is multiply this by this and then minus this divided by this. So it will be 4 into 5 minus 6 divided by 4. Okay, so this is 20 minus 6, which is 14 by 4, which is 7 by 2. Similarly, to find the coefficient here, right? So you will have to do 4 into k, this into this divided by this. There is no such term here, so basically you have to assume 0. So ultimately this will turn out to be k only. Okay, this into this minus this into this divided by 4, so it will be ultimately k. And what will be the power of s? Coefficient of s to the power 1. Again, same thing. This into this, which is 21 minus 4k by 7 by 2. Okay, and s to the power 0, this into this minus this. Again, here if nothing there, then assume 0. Okay, always this will come out to be k. Okay, now all this first row coefficient should be of the same sign for the system to be stable, right? So these are all positive numbers, so then k also has to be positive. So k has to be greater than 0. Also this has to be positive, right? So 21 minus 4k has to be greater than 0, means k has to be less than 21 by 4. So ultimately this is the condition for k. For this system to be stable, k has to lie in this range.